which is Dr. Hao Zhu. Our next presentation is going to be given by Dr. Hao Zhu, who's a tree fruit physiologist with Agriculture and Agri-Food Canada. And Dr. Zhu is also responsible for our local Summerland plantings of the NC 140 trials. She's been working on mitigation strategies for heat stress in tree fruits, and her update today will give us some of the information about the research performed in 2021. So Hao, I will leave it there for you to take over. Thank you.
Thank you, Molly, for the introduction. Hello, everyone. On behalf of our colleague, Jesse McDonald and Yoshi Watavani, Dr. Kirsten, Hannam, and I are presenting an update on our research on apples related to the heat waves that hit the interior BC in summer 2021. Due to time constraint, I will have to be brief on some slides, and we will have a longer presentation posted on Summerland Research Center YouTube later for your review. So like many tree fruit production zones in the Pacific Northwest, as the three presenters introduced, the Okanagan Valley also experienced a couple of sustained heat waves in last June and July, leading to massive forest fire and also crop loss in the tree fruit industry. Right after the heat waves, the sunburn, necrosis, and browning started to show up on many apples, particularly on the southwest side of the canopy. So in order to understand the mechanism underlying the heat damages and to facilitate early evaluation on the compromised fruit quality, we conducted a study on ambrosia and gala apple to characterize some external and internal characteristics after the heat damage. And we also evaluated the rootstock effects under the heat domes. So external characteristics, as Lee introduced, the sunburn browning is thought to be caused by excessive UVB radiation and high fruit temperature, surface temperature, about 45 degrees Celsius. So under the confocal microscope, Dr. Yoshi's lab captured the autofluorescence of chloroplast and vacuole in the fruit skin. So in the tangential view on the left, here you can see in the cells on the outer layer of the normal skin, there is abundant autofluorescence coming out of the chloroplast, which is filled with chlorophyll and autofluorescence as green. And also strong signals from the vacuole, which is filled with anthocyanin and shown as reddish purple. This is a normal, no damage skin. And under the moderately damaged sun browning skin, however, samples, there's still healthy cells, as you can see from the signals from the anthocyanin in the vacuoles, but you can tell that in these living cells, the signals of the chlorophylls has already degraded substantially. Some cells are dead, you can tell from here, which is a dark spot. Instead, it's filled up with another stress response compounds, which also autofluorescence in the green channel. And looking at these cross-section images on the right, you can tell easily that there is a cuticle layer in the no damage cells, in the moderate and severely damaged cells. So these structures, the cell structures under the cuticle, which is epidermal, you can tell in the no damage skins, the epidermal cells are intact. And with the damage, you can see the epidermal, the structure of epidermal is not is disturbed, or there are a lot of dead cells as well. And this kind of really strong autofluorescence green signals corresponds to what you see from here. This is this is just the top view where this is a cross section cutting through. So you can see a deposition of this stress response compound, which could be the melted wax, or it could be some sort of phenolic compound deposited in this tissue. This would change substantially on the spectral characteristics of the fruit skin under the damage. So using a handheld DA meter, we also detected some differentiations in the fruit skin absorbance between the 670 and 720 nanometer, where the fruits were still on the tree in August. We hope to use it to facilitate the early detection of the damage. Compare on the damage side, the sunlit side with the normal sunlit side, you can see the dirt absorbance is substantially higher in the damaged skin compared with the normal, and this is consistent in the two cultivars. As we know, the browning can be masked off during the coloration and maturation in the red cultivars such as Gala. And here, compared with Ambrosia, which is a bicolor apple, the red Gala, actually, this phenomenon is more pronounced in red Gala. So this is very promising. And the meter, although it's designed for detecting chlorophyll loss in the fruit skin, it can actually be a very helpful tool to detect subtle damages in the red cultivars in Gala as well. And the presenters have talked about the surface temperature, so I will be brief on this. So we use the infrared thermal imager to detect the minimum and maximum temperatures on the sunlit side on the damaged and healthy apple. And we found that the heat damaged fruits had larger surface temperature differences in both cultivar, in both Gala and Ambrosia. And this indicates the changes in the heat diffusion capacity of the outer layer of the damaged fruits. So moving on to the internal traits, we observed lower weight of the damaged fruits in the orange box plots compared to the normal fruits of in the green. And we also noticed a quicker weight loss during the ripening, during the first to third weeks of ripening. And fruit firmness is another important fruit quality attributes that we care a lot. We used a fruit texture analyzer to measure the firmness on both sunlit and shaded sides of the fruit. And this graph shows the differential firmness between the two sides. So in a normal fruit, you can see the differential value is close to 0, meaning that the firmness on the sunlit and shaded sides is fairly similar. Whereas in the damaged fruits, however, this differential is quite substantial. So the damaged sunlit side had a lot higher firmness compared with its shaded side. And when looking at the average firmness of the total of one single apple, we found higher average firmness at harvest in the heat damaged apple compared to the normal. And then we found a quicker loss of firmness during ripening in the damaged apple, so indicating a shorter shelf life. And looking at the dry matter content, we use the FedEx 750 to measure the dry matter content on both shaded side and browning side, and we found higher dry matter content on the damaged sunlit side compared with the normal sunlit side. And we also found lower tissue water potential on the damaged sunlit side and compared with the normal sunlit side. So both parameters indicates the damaged tissues were experiencing sort of water deficit. So since this heat stress is related to water stress, we wonder what role the rootstocks can play in terms of mitigating the heat stress. Although this is just 1 year data, but it's very promising. We recorded the ratio of damaged fruits in total count per fruit in the 3rd year leaf ambrosia rootstock trial. Compared 5 rootstocks, G202, G935 is relatively more vigorous. B9 is the smallest in the 5, and M26, M9, NIC 29 is sitting in the middle. And we noticed that the G935 led to the lowest ratio of damaged fruits in this 5. We also noticed similar tendency in the 3rd leaf NC140 Buckeye Gala rootstock. The more vigorous rootstock G4814, G969, and G935 had lower percent of heat damaged fruits compared with other less vigorous rootstocks. So Lee mentioned about foliar density, which definitely plays an important role. And we think the capacity of the rootstock in water transport also play an important role. So just a quick comparison between the B9, which is the smallest, and the G935, which is a semi-dwarfing, relatively large rootstock. You can tell the trunk cross-section area, the G935 is substantially larger than B9, and the root mass in the top soil layer, G935 is also roughly 30% larger than B9. And when we look at the rootstock xylem vessel elements, which is responsible for water transporting, their cross-section area, the G935 can be 70% larger than B9. So when the irrigation is sufficient, I think the more vigorous rootstocks would be able to transport more water to meet the demand of the xylem, and then that mitigates the heat stress. So I think rootstock selection can be considered and should be considered as a long-term measure to mitigate heat. And you probably wonder what we have as the immediate or short-term measures in the mitigation toolkits. So I will hand this to you, Kirsten.
Thank you, Hal. I think in the interest of time, we're going to skip over our slides for now, just to try and get us caught up. But we will record a longer version of these slides and post them to the YouTube website so that all attendees will be able to access them in the future. Thank you, Hal.
Okay, thank you, Kirsten.
Great. Thank you both, Hal and Kirsten. And as mentioned by Dr. Hannam, we will, since we have been recording these sessions, we will include those recordings as well as any other additional recordings that our presenters may make about some of the questions or other information onto a YouTube page that will be set up and available after the event. And we'll notify all of the attendees with an email link to be able to access those resources. So I just want to again thank you very much, Hal, for sharing your work and observations from this past season with us. If anyone has any questions for Dr. Zhu, please feel free to use the Q&A function. Dr. Kalsitz has provided a number of responses there for you to view from questions arising from his talk. So it's an opportunity. If you have anything that's come out of Dr. Zhu's work that you'd like to ask, please put it there. So thank you, Hal.